through a kind of tricky lecture with you today. And the purpose of this, from our notes, we were under D, Plinian eruption, as we're going through explosive eruptions, rocks, and textures. What I wanted to do is talk about how a Plinian eruption column behaves, but also what's going on in the conduit for a Plinian eruption, and starting from the magma chamber. And so to do this, we actually need to make a pretty detailed sketch, which is going to be hard to do unless we give ourselves the right amount of space. So what I recommend is you start near the bottom of the page, and I'm going to start down here, and we're actually going to work our way up through the earth as we go through describing the geology of this process here. So the first thing we got to do is, okay, we got to give ourselves space for the umbrella region here, and we're going to give ourselves space for the plume here, and we're actually going to, so let's go ahead and just start with the ground, and let's put in our volcano. And this is our volcano that is going to be having a Plinian eruption. Here is our ground surface. And as we go down into the subsurface, there's going to be a conduit that connects down to a magma chamber. Now I'm not drawing this part here to scale. I want this conduit to be really wide so I can draw bubble textures in it. And this, of course, connects to a magma reservoir, which is down here. But now our story starts with the ascent of magma. And as you think through, the keywords through this whole thing are going to be viscosity, density, right, rho's a symbol, and volatile solubility. These are the parameters that are going to be controlling the behavior of a Plinian eruption in the subsurface. And the first thing that starts is, as magma is ascending, pressure drops. So we're going to write a note to ourselves that says pressure drops as the magma is ascending. And as that pressure drops and magma is ascending, what is our effect? Our effect is that we've reached the point at some depth of volatile saturation, right, because of solubility. And so at this depth, bubbles nucleate and grow. As the bubbles are nucleating and growing, there are two effects that are going on here. One is that the density of the overall material is going down, right? Because as you add bubbles, you drop density. So let's say here that density goes down. If you want to write that fully out, go ahead and do that. I'm just, for space purposes and because I'm a little sloppy on this pad, I'm just going to do some shorthand. So bubbles nucleate and grow, and in response, density of the material drops. If density is dropping, there's more drive to ascend. And what that does is it causes some acceleration of our magma ascent. The other thing that's going on as bubbles nucleate and grow is that we're pulling H2O out of the melt. We're increasing the degree of polymerization. And so at this depth, viscosity must also be going up, which is our resistance to flow. So you can see that there's this balance between density going down, causing more acceleration, viscosity is going up, causing more resistance to the flow. So there's this battle that's going on in the subsurface between these two processes. At this depth, we're going to draw the bubbles getting bigger and bigger, and we're going to make a note to ourselves that things are accelerating. Specifically, the coupled bubbles and melt parcel is accelerating up the conduit. And at each step of increasing or decreasing depth, we here are going to have density still going down, and we're going to have viscosity. The symbol for viscosity is this weird N shape, is going up. The magma is becoming more and more bubbly, until at some point it turns into essentially a froth. A froth would just be another word of saying pumice. And at this point, when it is so bubbly and so much melt has lost the volatiles, it's so viscous that it can't handle the deformation, the strain that the ascent is requiring. And we reach this tipping point. And so we need to put this in our notes, because this is the point of, let's say the words, brittle fragmentation. The depth of brittle fragmentation is another way of saying the explosion depth, the actual depth where the eruption occurs. And what I want you to say next to brittle fragmentation is something along the lines of the viscous melt can no longer accommodate strain from ascent. This is our tipping point. And I'm going to put in a red jagged line to say we have just fragmented the melt. Everything shatters. The gas is released. It had been constrained by the viscous melt beforehand, all that gas inside the bubbles, and now it's just been explosively released. And so it accelerates and shoots out of the conduit and out of the vent as this dusty jet of gas. It's like a freaking jet engine, to be honest, okay? And it is just blowing out, and it's so fragmented. That's what I say, dusty jet. When I say dusty jet, you're going to picture just ash surrounded by gas that's moving at 100 to 600 meters per second. Here, we're maybe ascending at 10 centimeters a second, and here 600 meters per second. That's how much acceleration goes on at this point of brittle fragmentation, which is why we have an explosive eruption. So as we go to our drawing, we need to draw this material just firing out like rockets out of the crater. And what we're going to call this region, that's firing out, this is called the gas thrust region. Material in the gas thrust region is, some material is ballistically getting emplaced as it loses its momentum and falls to the ground. Other material is being shot further up into the atmosphere. But importantly, within the gas thrust region, the density of the material is greater than the density of air. And if the density of the material being shot out of the volcano is greater than the density of air, well, it should all rain down to the ground. And that can't explain why we get this column that rises up into the atmosphere. So let's go ahead and add something like this. And what this is a convective region. And this is called so we're going to call this the convective region. And this is also known as the eruptive column or plume. So we're going to call this the plume. This also is sometimes called the column. And okay, so we have the gas thrust region, that's like about to here. And then the convective region is this part up here. And the density, okay, it's all about density here. The density in the convective region, we have the density of the actual column is less than the density of the air. And what this allows for is ascent, right? Because it's going to buoyantly rise because it's less dense. And the reason why that happens, maybe this is getting a little too detailed for you, but atmosphere gets ingested. Okay, this blue line here, this is showing just normal atmosphere. Atmosphere. We're going to use the word ingested. It gets pulled into this rising, convective, turbulent mass of ash and hot gas, and it gets heated. And as the atmosphere gets heated, its density goes down. And so we have this another runaway effect, whereas we pull in more atmosphere, we heat it, we get more buoyant drive. And so let's put a couple words here. Let's say something like plume ingests atmosphere and heats it. The mixture becomes low density than the atmosphere, and it rises. If you need anything like that, go ahead and put it. Now, what is our speed? Let's say our speed here is about 10 meters per second. Down here, our speed, so it's slowing down because down here it was like 100 to 600 meters per second. But it's still rising quickly up into the atmosphere. And it'll continue to do that until it reaches a level of neutral buoyancy. So we're going to put in a dotted line here. And we're going to call this level of neutral. I always struggle to spell that word. Buoyancy. And at the level of neutral buoyancy, the density of our eruptive column is equal to the density of air. And so it no longer rises anymore. So have your column come up to this, and then what's going on in the atmosphere always? Well, there's always prevailing winds, and our prevailing winds are going to blow our column. So we're going to have our column do this, and this area up here that I'm drawing in right now is called the umbrella region. So this here, we're going to call above the level of neutral buoyancy is called the umbrella region. And the important bit about the umbrella region is that it's driven by prevailing winds. So let's say driven by prevailing winds. And this is how the ash gets distributed across the globe. The other thing that's going on, we can make it more artsy with some eddies still, because we're still ingesting material, air, but we're also doing something else. We're starting to, because of gravitational settling, we're going to put some arrows coming down here. Ash that's in this eruption column can't stay supported, and it starts to settle out and rain out, and it'll form a blanket that then gets deposited on the earth. Okay, maybe your drawing's starting to look a little cleaner here, but what I wanted you to have is some ash settling down from the umbrella region, and we're going to call this gentle gravitational settling of ash. Gentle gravitational settling of ash. And this could be within the kilometers closest to the volcano, or it could actually be blown around the entire planet by strong winds, and you get ash that deposits hundreds to 1,000 kilometers away. Okay, so what we've just described is how we can get the gas thrust region propelling material, and then atmosphere gets ingested in and heated, which drops the density of the entire eruption column so that it's lower than that of the ambient atmosphere, allowing the eruption column to ascend to heights within the troposphere and stratosphere. Eventually we get to a level where the density of the atmosphere is the same as the density of the eruption column, and it can no longer rise further. That's the level of neutral buoyancy, and then the prevailing winds take the umbrella region and blow it away. I hope that's explained it to you. Take a look at the textbook if you need any more descriptions. It's certainly an exciting topic, and maybe will make you want to take volcanology classes later in your academic career. Well, there's one last thing we forgot to do in this schematic, and that is what happens if we don't ingest enough atmosphere and our density always stays greater than that of air. Well, what can happen is the column, here's what we're going to do. If the column does not ingest enough air, we can actually create an avalanche of hot gas and ash called a pyroclastic density current that will roar down from the column, down the sides of the volcano, and across the surrounding landscape. This is called a PDC, a pyroclastic density current. And these are the two ways that rocks form in response to a Plinian eruption. You get the either gravitational settling, called a pyroclastic fall, or a pyroclastic density current. And so what we're going to do to finish off our notes is we're just going to put some information about these two different things. And we're going to just make a little heading here called falls versus flows. And under falls versus flows, let's talk about each. So we're going to talk about pyroclastic fall material. And this is an actual rock type that you'll find out in the field. Maybe you'll see hand samples of it in your lab. And what these do is this forms from the gentle gravitational settle from eruption column. The pyroclastic fall materials, you can recognize them because they're always really well sorted, because that gentle gravitational settling provides an environment that's not, well, it's not very highly energetic. And so they're very well sorted. And the other thing is they fall like snow. And one thing snow does, just like ash, is it mantles the topography. just forms a layer that forms a blanket. So what do I mean by that? If this is like our topography and we have a layer of pyroclastic fall material, it will just form a uniform blanket that covers topography, and it'll always be really well sorted. Let me see if I have a picture of that. I don't even have a picture of that to show. I think most people have seen snow fall, and so you get the right idea. And so our grain size in the pyroclastic fall is controlled by two things. It's controlled by how proximal you are to the volcano. Let's say that in a simpler way. Let's just say controlled by distance. Bigger material, so if here's our volcano, right? So bigger material can settle out closer to the volcano if we were to like look at the sorting. Whereas if you go further and further away, that material can't stay in the atmosphere as long, and so you get this gradation in terms of grain size. All right, so in part, grain size is controlled by distance, and it's also controlled by eruption power, or like the amount of fragmentation. Eruption fragmentation. Very powerful explosions will actually produce finer material. So that would be a way to interpret the rocks that you see, just using grain size to tell you something about how close you are to the volcano or how powerful the eruption was. Now, the other type of pyroclastic rock that can form is from a pyroclastic flow. Oh boy, that's not how you spell flow. Flow. Now, pyroclastic flow is a vocab that is no longer as in vogue. And so instead, what the community calls these are pyroclastic density currents, which is a total mouthful. So then no one actually even says pyroclastic density currents. They just use the acronym PDC. And I hate acronyms. And so I don't care if you call them pyroclastic density currents, pyroclastic flows, or if you use PDC. They all mean the same thing. And this is a density current, which is another way of saying avalanche. Right? This is our avalanche of hot gas and ash that forms from column collapse. All right, so let's talk about the formation of a pyroclastic flow. In fact, before we do that, I'm going to throw a picture in. Here's a good picture of a volcano with an eruption column. Here's the eruption column. It's trying to rise up past the gas thrust region into the eruptive column region. You see that it never makes an umbrella region because it doesn't ingest enough ash, and instead the density always stays greater. So in this case, we had collapse because density stayed greater than the density of air. And we get this avalanche of hot gas and ash roaring down the side of a volcano, burying towns, killing people. This process has killed hundreds of thousands of people in the last few hundred years. So this is the real dangerous thing about volcanoes. So let's say something like this. Let's say this is an avalanche of hot ash and gas that forms by column collapse. That's the primary mechanism for how you produce a PDC. However, if you go to the last few lectures about silicic lava domes, and if there is an oversteepened edge of a lava dome and that collapses, that also makes a PDC. So we're also going to have a second mechanism here that connects back to effusive lecture, and we could say, or by collapse of steep lava dome. Those are the two ways to make a PDC. To recognize a PDC in the rock record, we're going to look for two things. We're going to look for very poor sorting. It's an avalanche. Avalanches are always very poorly sorted because big clasts and small clasts are all mixed together. So here's an example of a PDC deposit that's been incised by some river erosion. And if we look at this in detail over here, we can see these huge blocks and boulders all supported by very fine ash. So we're going to look for very poor sorting. Another thing we're going to look for is that it fills valleys. It doesn't mantle topography. Instead, if this was our topography, the PDC would actually be sitting in the valley as this very poorly sorted deposit. It behaves like a river or a mud flow in that way. And then the last thing to talk about is the textures that we expect to see in these rocks. So one of the textures, I guess I've already noted. So let's see, we can go. Here's an example of a closer zoomed in view of a PDC, of a pyroclastic density current deposit. And we see large clasts, and then we see areas of ash. And so we see that very poorly sorted. But this is a pumice. And pumices are very weak. And if all of this stays really hot and this deposit gets very thick, filling some valley, you'll actually put a lot of pressure on these pumices, which can flatten the pumices into a texture that looks like this. We call this welding, or we call it flattened pumice. And so the texture we're going to see besides very poor sorting is we're also going to look for evidence of welding. And evidence of welding can look like flattened pumice. A flattened pumice is, so if we had like, here's a big chunk of pumice with all the bubbles, but then it experiences pressure while it's still hot, it will flatten to something that looks like this. And this texture, right, hopefully it looks something like this in this picture, this is called a fiamme. And a fiamme means flame in some language that's not English, and this is evidence, or this is flattened pumice. That's what fiamme is. This is also sometimes referred to as eutaxitic texture, just in case you see that in the textbook. It's the same thing. It's just the texture formed by welding. And this can be seen in hand sample, in outcrop, even in thin section. What if you had a tricuspate bubble shard that gets flattened by welding? Well, you might see something that looks like this in thin section. All right, so that's something to look out for as you recognize explosive rocks in the field and in hand sample.